All right. Let's talk more about modular arithmetic. So you have the Euler totient function. Let's go back to modular arithmetic. So we talked last week about modular arithmetic in terms of shift ciphers, which that is great. It's wonderful. It's huge. But modular is more than just shift ciphers. In fact, most of modern cryptography is based on some kind of modular arithmetic, which is part of the both positive and downfall. See, modular arithmetic, in case you haven't figured this out, figuring out inverses is you can do it with the obviously the Euclidean algorithm. We can figure out inverses, but I need to know what they are. And there's some other things that also why modular arithmetic is critical for ciphers. So let's just understand something about taking powers of a number, large powers. And I mean like super large. You're thinking like raising to the 100. No, no, no. I'm talking about thousands. So let's talk about RSA and the Diffie-Hellman encryption. Those are two examples of how this ends up being. Now, the naive method, if I ask you to compute something to a power, is you compute that thing to a power and then you take it mod n afterwards. That way you do the exponent and then you do mod n. That's how most of us think about doing these sort of things. That is flawed. And here's to understand why. So I want you to try computing 3 to the 10,000th power. And just to kind of visualize this a little bit more, let me actually switch. Let me show you an example. So I'm switching here. I'm using a Jupyter notebook. For those who don't know, Jupyter notebook essentially is a Python. And it's really nice. I can load whatever libraries and I do a lot of data analytics in my Jupyter notebooks. So it's an IDE. It's all it is. Okay. It's a way to package all up your code. So I want to just take 3 and I want to take it to the 10,000th power. Now I'm going to tell it to run. And notice it immediately comes back and gives me an error. And the reason being, if I come all the way down here, is because it exceeds the length. It has a max length for integer strings because it actually doesn't want to round it and then do an exponential form. It wants it exactly because that's how it does its math. So, however, if I trim off one of those zeros, see, it does it. I mean, it's a huge number, as you can obviously see. Lots and lots of digits. So the question is, how do I deal with this? If I can't just compute 3 to the 10,000th and then take that something, how am I supposed to be able to do these really large powers in modulo? Well, let's go back to the slides to kind of see that. So we've already seen that this is not something that's going to work. By the way, trading on your calculator will throw an error just as much. And we do use numbers this size in modern cryptography. So how do we do it? We do what's known as a binary expansion. So let's do a much smaller example because I could do this on 3 to the 10,000, but let's do a much easier example just to kind of get this across. So I have 3 to the 217. Yes, I know you can calculate 3 to the 217, but instead let's start with 218. Let's take 218 and I want to break it into the powers of 2. In other words, I want to write this in binary. So for those that are unfamiliar with binary, which is a total shame because you're all computer scientists. In binary, if I was to write the number 1001122, I can't do 23. Ooh, that's a bad. I only have zeros and ones, but what does this really mean? So if I do the 1 base 2, this is how sometimes we write it. Well, this right here is 2 to the 0 power. This right here is 2 to the first power. This right here is 2 to the second power. This right here is 2 to the third power, and so forth and so on. So I'm actually doing a binary expansion. I'm turning this into binary. I'm writing what are the powers of 2 that I could do this, a sum of them. So and the way we often do this is say, what's the biggest power of 2 that's less than 218? And the answer to that is actually going to be 2 to the 7th. So if I take 2 to the 7th, and then 2 to the 6th, and 2 to the 4th, and 2 to the 3rd, and just 2, which is 2 to the 1st, mind you, and add all of these together, I get this answer right here. Well, that's really cool. So I just got something that that tells me exactly how I can write 218 as a binary number. So this, and be aware, this actually would be the 7th digit. This has to be 8 because 2 to the 0 is the first digit. We start at index 0. So if I was to write this in binary, for all of you that want to see this actually as a binary expansion, again, because you can throw binary expansion in, it does stuff really quickly in computers, but this would give me a 1 for 2 to the 7th, 2 to the 6th, no 2 to the 5th, 2 to the 4th, 2 to the 3rd, no 2 to the 2nds, a 2 to the 1st, and no 2 to the 0s. This is what this number is in binary. Okay, so that's what it is if you hit binary expansion in your, and that's an easy function inside of Python for all of you that love Python. Okay, so if we do this now, our rules of exponents tell us that this sum, since I can now write 218, since I can write that as a sum of values, namely this sum, then this is 3 to that sum. But the sums then break up as 3 times 3 to the squared plus 3 to 2 to the 3rd plus 3 to 2 to the 4th. Sorry, not times 3 to 2 to the 4th times 3 times to 2 to the 6th times 3 to 2 to the 7th. I know I have exponents in my exponents, but trust me on this one. Now, why do I do this? Here's why. Because computing this. So how do you get from 3 to 3 squared? You square it. 3 to the 2 squared means I'm going to square it again. So this number is simply the prior number squared. So I take 3 squared and I squared it. This would be 81. Then I would take 81 squared and it gets me here and so forth and so on. So doing each of these is now actually super easy. And notice these are 2 to the 0 power, 2 to the first power, 2 to the second power, 2 to the third power. Now we have this. So we start with all of these kind of concepts, and next we come here. Now we make a list. What's 3, 2 to the 0 power? Well, 2 to the 0 power is going to be just 3 to the first power, which is 3. 3 to I is 3 to 1, which is 3 squared is 9. Squared, you get 81. Now this is the fancy part. I'm taking this mod 1000. So 81 squared. What is 81 squared? And we can quickly just sit here and ask these questions. 81 squared, it turns out, is 6,561. So let me write that out real quickly because you can realize what's actually going on between these two steps. So this step, what I did was I took 81 and I squared it, and then I took that mod 1000. So this came out as 6561 mod 1000, which is equal to 561. So that is how we only had 561. Now to go the next step, I just do what's 561. I'm going to square that, and then I'm going to take that mod 1000. Why am I doing this? Because the truth is this is keeping the numbers relatively small. Even no matter how close I get, even when I get all the way up here to a number that's pretty close to 1,000 and I square it, it's still going to keep it pretty small relative to my modular realm that I'm already living in. So this is why we do these things. We're going to square and raise and square and raise. And I only have to go, because remember, my biggest power I had was 2 to the 7th. So I only have to go that far. I don't have to go. So I have to run this. So let's see how many steps that I have to do. So each one of these I'm squaring, and then I'm taking it mod 1000. And I'm going to show you in a second. That makes this actually super efficient because we actually only had to do in here. I didn't have to do anything here. So I took the 3. So I squared into thousands. So that's 2 steps, 4 steps, 6 steps, 8 steps, 10, 12, and 14 steps. I've done 14 steps just to create this table, 14 calculations, because each one is squaring and then taking that mod something. So it's actually doing 2 steps. So this is equal to this. Now notice we know 3 squared. It's 9. 3 to the 2 to the 3rd. That's this one right here. So it's 561. 3 2 to the 4th is right here. So I get that 721. 3 2 to the 6th, over here, the 281, and the 961 for 3 to the 2 to the 7th. I can multiply all these together. And again, computers don't multiply them all together in the same time. They do They do them in pairs. So they do this times this, then times this, then times this, times this. So far I have done 14 calculations. Then I'm going to do 15, 16, 17, 18, and take that mod 1000. So I've done 19 calculations to get the answer to this thing. Now, if I was to take this to the traditional method of raising this to the 218th power, if you technically tell something to take a computer just in general, it does a recursive formula. 3 to the 218 power goes 3 squared times 3 times 3 times 3. It multiplies itself times 3. So it actually have to do those steps. So just to write that down, this method that we just did, we just said, let's say at 14, we said 15, 16, 17, 18, 19 steps. So our method, this new method, had 19 steps in it, 19 calculations. Comparatively, if you did the traditional recursive powers, this would have 218 or 217 multiplications plus one mod at the very end. 19 steps or 218 steps. Which do you think is a better one? I'm going to go with the 19 steps. So this rate of doing exponential powers in modular arithmetic is actually the crux of how we do modern cryptography. Now, along with this, we need to talk about prime numbers. Now, I know you probably know what prime numbers are. Prime numbers are any number bigger than or equal to 2, not 1. 1 is not a prime number. Do not mess with that, okay? Any number bigger than 1, whose only positive integers are 1 and that number. That's the only things we have. So we have a really cool theorem, though, that says that if P is a prime number and it divides a product of numbers, A and B, then P must divide A or P must divide B. It could potentially divide both of them, but have to divide at least one of them. That's really, really powerful. Further, we have a really, really powerful theorem that we are going to leverage. It's this. Any number can be written as essentially a bunch of primes, P1 to some power. So let's say P1 is 2. I take all the 2's out, and that's gonna be that alpha 1 up here, right here. P2 would be then a next prime number. So it could be 5, and be how many 5's do I have in here? Pull out as many and so forth. The only thing this is unique outside of the order in which we write the P1, P2, PK, we can rewrite those. However, the powers associated with each number are very, very specific, and that does not change. And they're bigger than or equal to 0 for every one of these things, meaning they're at least one of them. And this is sometimes known as a prime factorization of a number. There is one unique way to do it. So when we do this prime factorization, we get something called the order of P. That is going back. It's all these alphas. It's all these exponents. So the order is kind of important. And when we get that, it's going to help us out because we're going to have to deal a lot. I have some cool theorems to come up later in this week about that. But I want you to think about this for a second. I want you find a prime factorization. So this is the rest of your discussion board challenge. Find the prime factorization of 1728, and I want you to write down what are the orders, remember that's the powers, of that factorization. Finally, how hard was that factorization? Think about that question while you tackle it, and I'd love to, and that's going to be your other question to answer on the discussion board.